Hello, pirates and other internet explorers. Today we are going to be doing a brief discussion of bonding and energy, and especially in terms of covalent bonds. If you remember, covalent bonds are a bond between two nonmetals who are sharing those electrons. Sharing is caring, because both of those atoms involved in the bond want to gain electrons, and since both of them can't both gain, then therefore they share. So what does this have to do with energy? Well, let's use a little bit of a metaphor. Let's say I have a flat surface right here, and I have a bowling ball right here. Okay, and I take that bowling ball and I put that bowling ball up on a ladder. Now, in order to put that bowling ball up onto that ladder, I need to add energy into that bowling ball. I have to put energy into the system of the bowling ball, and I put it up there on top of that ladder. Now, so I add energy to that, and when I do so, the ball gets higher, right? I lift up the ball, put energy into the ball, I lift it up higher. Now I store that energy as potential energy for those of you that took a physical science. And when I do this, what I've done in this all essence is I've taken a ball that is very stable, right? It's stable on the floor. It's not going to do much as long as I don't put extra energy into it. And I put it up here on the ladder where it is unstable. And that means that something could happen to it, right? If I bump into that ladder, what's going to happen to it? Well, that ball is going to fall. So let's say I did bump into that ladder. When I bump into that ladder, it goes back from being unstable. It goes back from being unstable to stable, right? It goes back to being stable. And when it does so, it can cause a lot of damage, right? And that's because it is releasing its energy as kinetic energy into the surroundings, into the environment, right? So I add energy into the ball, I put energy into the bowling ball, put it up high, and make it unstable, right? That ball can be knocked down at any time, and when that ball gets knocked down, it returns to being stable, and as it's going from being unstable to stable, it's releasing energy into the surroundings, right? So let's look at this another way, right? Let's say I take the same bowling ball, and instead of putting it up on a ladder, I put it up on some stairs. Okay, so I just got some prop stairs in my room, right? So I put all of this energy into the bowling ball, right? And I let that bowling ball up there, and I've made it gone from stable to unstable, right? And now I bump into the bowling ball, and the bowling ball falls, but it doesn't fall the whole way down. It only falls in this first step right here, right? What I've done, in essence, is I've added energy to the bowling ball to make it unstable, right? And then when I knock the bowling ball, it only falls on that first step, so it can still continue to fall. It is not as stable as it started off, but it is more stable than what it was when it was on top of the staircase right there. Also, when it loses energy to the surroundings, it's not going to lose as much energy as I put into it. It still has energy that it could lose. I can knock the bowling ball down again, and I can lose a little bit more energy, and I can knock the bowling ball down again, and I can lose even more energy until it's completely stable. Okay, so as you can see, you put energy into it to make it unstable. When the bowling ball then falls, it releases that energy to the surroundings and becomes more stable. Well, what does this have to do with covalent bonds? Well, if I have let's say I have two atoms, right, that are bonded to each other. Let's say I have two fluorines. They share one covalent bond between each other, right? They are stable, right? If I break that bond, in order to break that bond there, I have to put energy into it, right? So I have to add energy to that bond to get it to break. Right? I add energy into that bond to get it to break. And when I do so, I make these unstable, because what I've done in all sense is I've broken that bond. Right here, they're happy, right? Because they have 8 valence electrons each. 2, 4, 6, 8. 2, 4, 6, 8. 8 valence electrons each. The fluorines are happy when they are bonded together. They are stable. And I've broken that bond, and I made them unstable, because right now they only have 7 electrons each. And as we learned way back in Unit 1, atoms want those full octets, and so they're going to do a chemical reaction until they get that octet. So let's say I stop putting energy in. What's going to eventually happen, if there's only fluorines involved, right, if there's only fluorines in that area, then those fluorines are going to reconnect, and I'm going to get that energy back again, and it's going to lose energy into the surroundings, and it becomes stable again. So it goes from stable to unstable, right? I added energy to it, and then it loses energy, right? The fluorines lose energy to the surroundings, and they become stable again. Okay, so here is the cool thing about these energies. Now you can do calculations based on these, but you can figure out how much energy it takes for each one of these bonds to become unstable, or how much energy it takes for each one of these bonds to become stable. So when you break a bond, you add energy, you make it unstable. When you make a bond, you release energy, and you make it more stable. Every single bond kind of has different levels of instability, right? Some atoms are more reactive than other atoms, and so therefore, when you when you have different bonds, you're going to have different energies. So it's really simple and really straightforward to look up how much energy it takes to make a bond and how much energy it takes to break a bond, and we give you a table. And all you have to do is figure out what bonds you have, and then you can figure out what the bond energy is. Now, the bond energy is the energy it takes to break a bond. Okay, so you put energy in, you break the bond up, or it could also be the energy that is released when you make a bond. Okay, so you make a bond, you break a bond, you add energy, you make it unstable, you make a bond, you make it more stable, and you get the energy back. So let's say I have a bond between a carbon and a carbon, right? I have a bond between a carbon and a carbon. All you have to do is look on this chart here. You look at it is a single bond between those two carbons, right? So the energy it takes to break that bond is, here's my first atom. I look it up on this chart side here. Here's my second atom, a carbon, right? And I just look, and right there, that energy it takes to make that bond is 83 kilocalories per mole. So that is the amount of energy it takes to break that bond, but if you're making that bond, that's also the amount of energy that gets released as you make that bond. All you have to do is look up the bond on these charts. So here, for example, it's a double bond. I'm going to change my highlighter so you can see it's a different color. I have a double bond, so I'm going to look here at the double bond energies. And then I go through the list, and oh, here's a C double bond O, and so the amount of energy it takes to break that double bond is going to be 185 kilocalories per mole. Okay, the amount of energy you get back when you make that bond is going to be 185 kilocalories per mole. It's simple, it's straightforward. All you do is you look at your two atoms and you look at what type of bond is in between them. So if I have a single bond between a silicon and a oxygen, I look up my first atom here, silicon. I look up my second atom here, oxygen. Uh-oh, boom. It shows me an X. Well, if that happens, all you have to do, because what we've done is we've listed these in order of electronegativity, so if you cannot find the element in that regard, if you have an X, then look it up the opposite way. So in this case, I'm going to look up the oxygen first, and then I'm going to look up the silicon next. And actually, sorry, it's not in order of electronegativity, it's in order of atomic weight. So therefore, we have the oxygen and the silicon, single bond, and you have 108. So that's all you have to do, is look up the elements within that bond, look up the type of bond and look it up. If I have a triple bond, for example, a C triple bond nitrogen, you look it up on the triple bond energy chart, and that's how much energy it takes to make the bond. You put the energy into the system, it breaks the bond, and if you're making the bond, that's the energy you get out of the system. It's going from stable to unstable, or it's going from unstable to stable, right? You break a bond, it's becoming unstable, so you have to add energy to it. You make a bond, it's becoming more stable, so you have to release energy. You're losing energy from the system. All right, if you have any questions, concerns, or comments, ask your teacher. We'll be more than happy to go through. Next video is talking about how you can use these bond energies to do calculations within a reaction by looking at both the reactants and the products of a reaction. All right, see you next time, Pirates.